We're waiting, yes, for the mic to also get picked up here. Excellent. Good afternoon, everyone, and welcome to the Delft University of Technology, and more specifically, welcome to these lectures for the matching and selection procedure of the program of Computer Science and Engineering. For those of you in the room, welcome to our campus. For those of you watching at home, hello, welcome to the live stream. Glad that you're joining us online. For today, we have two lectures in store for you. First, by my colleague, Nick de Klein. He'll be guiding you through some of the mathematics problems that you've already prepared for today, we hope. After that, we'll have a 15-minute break, roughly 15 minutes, after which I will take over. Hi, my name is Stefan Huchtenberg. I'm a lecturer in the Bachelor of Computer Science and Engineering, and I will be talking to you about reasoning and logic, which is a first year, first quarter course here, and also one of the parts of the CST, the cognitive skills tests. But first of all, time for calculus. Nick, the floor is yours.
All right. Good afternoon, everyone. So I'm Nick de Klein. I teach in the first year, I teach calculus at least, and some other courses as well that you'll meet later on. For the test, there is some mathematics there, and it is all sort of working up towards what we're going to do in calculus, but it's going to be pretty mild, right? And we're going to start easy as well. So what I wanted to do today is just go through those exercises. There are 7 exercises that you've prepared for today. Just go through them step by step, and also maybe give some indication of how to approach those kinds of problems, right? So we'll start with the first one. The way I'm going to do it is I'm just going to write it here on the board. I'll look at it. I'll say about what the strategy is going to be, and then work it out, okay? So if at any point you have any questions, then just raise your hand, and you can ask that question, right? So you can interrupt me at any time for questions. All right, let's get started then. So the first question was about finding some number alpha such that an equation would hold for any positive x. And the equation was the following. The reason that we're looking at positive x here is because we also have some square roots, right? So that wouldn't make much sense if we had negative numbers, right? Plus we have some x's here in the denominator of fraction, so that also wouldn't make much sense if x equals 0. So we better keep with positive x, but that's no problem. So this question is really just about working with exponents, right? So work out both of these terms are actually just very convoluted ways of writing x to some power. So there's basically 2 ways to go about it. The first way we'll cover is, all right, let's write both the left and the right-hand side in terms of x to some power. So we'll get some power on the left, we'll get some power on the right. Then if we equate those powers, we find alpha such that that equation holds. Voila, we're done, right? Because then both the left and right-hand side will just be x to the same power, which is always equal. So how do we do that? Well, we have some products and quotients here, right? So we have, first of all, this x to the power minus a half, and then divided by x. Dividing by x is like multiplying with x to the power minus 1. So that's sort of our first step here. Then dividing by x to the power, or square root of x to the power alpha, that would be multiplying by square root x to the power alpha to the power minus 1. And a square root is a power a half. So in the end, we're multiplying by alpha to the power minus a half. Okay, we can do some more simplification here because now we can bring them all together. First of all, here on the final x, if we have a power to a power, then we just multiply those powers, right? So we get x to the power minus alpha over 2. And then also, if we multiply through exponents, then we add the exponents. So in total, we'll get here now what will happen during calculus a lot is that I'll make a mistake. So if you see me make a mistake, then let me know. But I think this is correct, right? So if you take minus a half minus 1, that's minus 3 over 2, minus alpha over 2. So in total, we get minus alpha plus 3 over 2. On the left-hand side. So we play the same game on the right-hand side. Again, we have this x cubed. Dividing by x is multiplying by x to the power minus 1. So that's x minus 1. Dividing by square root of x is multiplying by square root of x to the power minus 1. But again, square root is just to the power a half. So that's times x to the power minus a half. And then again, here we have a product of exponents. We just add the exponents together. So we get x to the power 1.5. Right? So our equation becomes x to the power minus alpha plus 3 over 2 equals x to the power 3 over 2, which yields us that equation that I was talking about, namely minus alpha plus 3 over 2 equals 3 over 2. And that's now just a simple linear equation for alpha that we can solve step by step, right? So if we multiply both sides by 2, we get minus alpha minus 3 equals 3. Right? Does that make sense? Yes. Then we get minus alpha equals 6 by adding 3 to both sides. And then we get alpha equals minus 6. All right. That's it. Yeah. So the question was, isn't it minus alpha plus 3? And the answer is I should be more careful, put my brackets a little bit, maybe put some brackets in. So there are sort of brackets here, right? So it's alpha plus 3 all negated. Here as well. And so that's why we get here minus alpha minus 3. All right, so there was one more thing I wanted to show here. So this is one way of going about it. It's a perfectly fine way. But just to get another topic sort of under our belts here at the beginning, I also wanted to show that you can get that equation by applying a logarithm to the whole thing. That's mostly for fun. I'm going to take a new page. We can apply logarithm to this entire thing, and then we can consider our rules for logarithms. In particular, we have a few interesting ones, namely the product goes to a sum. Similarly, a quotient goes to a difference. And if you have exponents, then they come outside of the logarithm. And I'll let you work out for yourself which values of a and b we cannot consider here, right? Because the logarithm, you can only take it of a positive number. So for instance, we want a and b here to be positive. Definitely don't want b to be 0 anyway, etc. Although over here, for instance, it's okay for b to be negative. So if we apply these rules, what do we get here? Well, first of all, we have a quotient, right? So we get logarithm of x minus a half minus logarithm of x times square root of x to the power alpha. Then here we have an exponent, so we get minus a half logarithm of x. Here we have a product, minus logarithm of x. And then we have another exponent, alpha over 2, right? Square root of x to the power alpha is just x to the power alpha over 2. So we get minus alpha over 2. Which in total then gives us this. And again, to be clear. All right, you guys know these by heart, right? I imagine. Yeah. And I can get rid of them here and put the other side through the same treatment. Again, we have a quotient. And then here we have an exponent. And here we have a product, where the second part of that product is an exponent. And so you see again that if we equate these two sides to each other, where we just applied the logarithm to the whole equation, then they were both some coefficient times logarithm of x, and equating those coefficients gives us back the equation that we saw earlier. Right? So this is doing exactly the same thing, only once with exponents, once with logarithms, and the only reason to make you go through it twice is because now I also told you about the rules for logarithms, which you do need to know. All right. Any questions about this first one? Yeah. Why didn't I do what? Because I thought it would be more work. And because I want to tell you about exponents and logarithms and not so much about cross multiplication. But that's a fine approach. So the question was, if you equate these, then you can cross multiply them, and then you also get two sides that are just products. And the reason I didn't do that is because I want to actually bring home the fact that you already had two sides that were just products. Does that make sense? Perfect. All right. Let's get another one. A different color. All right, so question 2. Question 2 is just quickly to get going with trigonometric identities. So the question there was, to write this quotient, sine squared of 2t divided by cosine of 3t, as a quotient that only contains references to cosine t, but not to sine of anything, not cosine with some other frequency, just cosine t. And so what that comes down to is just doing a bunch of rewriting by applying trigonometric identities again and again. Now, it's very useful to know these trigonometric identities by heart, because then you can go through these things kind of easier, right? However, they are also on your formula sheet. So if you forget them, then you have them available on the formula sheet, which is, I have to say though, a little bit more expanded than the formula sheet that you see in calculus, the one for the selection test. In particular, what we're going to need here is the doubling angle formula for sine, right? Because you see here sine of 2t. Now, if we want to find something in terms of only cosine of t. If we have something in terms of sine of t, that's kind of fine because by the formula sine squared plus cosine squared equals 1, we can always kind of massage it back into cosine of t. But that 2t here, that doesn't disappear without a doubling angle formula. So we're going to have to apply that. And this is one that you can find explicitly on the formula sheet. The sine of twice t equals twice sine of t cosine of t. So that's it, right? That's the doubling angle formula. If we plug that, so we'll just start by plugging that one in. Say, do I want to do that? No, I'm going to work out the numerator and denominator separately. I think that makes more sense. All right, so that means we'll need a square on top of here, right? So just square this thing, which actually works to our advantage here, because if we square this thing here, then we'll get a sine squared, and that one's even more easily written in terms of cosine. Right, so I have here 2 sine squared, and as I mentioned, sine squared plus cosine squared is 1. So sine squared itself is just 1 minus cosine squared. Cosine squared. And of course, 2 squared is not 2, but 4. Right? All right. So we get this, and that's okay, right? That's already in terms of just cosine. Right? So if we just up here say we're going to call cosine, we're going to call that c. Then we can simplify this a little bit if we want. We get 4c squared minus 4c to the power 4. So here, at least in the numerator, we're going to get that. Right, 4c squared minus 4c to the power 4. Then we need to get working on that denominator. So we'll need a tripling angle formula. I don't know if that one's explicitly on the formula sheet. I don't think so. But there is just the trigonometric identity for adding angles within the cosine. So we can just use that one. Or you can just say that 3t is just 2t plus 1t. And there you have it. So that would mean we get cosine of 2t times cosine of t minus sine of 2t times sine of t. And then we can use the doubling angle formulas again to keep going. How does this work again? With me? The really? No, I want more. Yes. Ah, there it is. Okay, thank you. All right. But my grid lines are... All right, so the doubling angle formula then for the cosine. So we just get cosine squared t minus sine squared t times cosine t minus twice cosine t. There. Right, so that's twice cosine t sine t times that other sine t gives us sine squared t, which again is very good because that nicely writes down to 1 minus cosine squared. So that here we get, right, so we get here cosine squared minus 1 plus cosine squared. Well, that's 2 cosine squared. Minus 1. There we go. Yeah. So in total, what I get here is 2 cosine to the power 3, plus another cosine to the power 3 from there, or plus another 2 cosine to the power 3 from there. So that gives me 4 cosine cubed. And then I get here minus cosine t, and then here another twice the same thing, so minus 3 cosine t. Right, so in terms of c, that's 4c cubed minus 3c. Voila. It takes a bit of doing, but in the end, you get there by just applying your trigonometric identities. And then we can simplify this a little bit by dividing out one of these c's, right? So you just get 4c minus 4c cubed divided by 4c squared minus 3c. Voila. Did not do it. There we go. Voila. Right? And the upshot of this question, of course, is just if you've got can you apply these trigonometric identities? Sometimes you have to combine them. In this case, we used only 3 in the end, or I guess 4, right? We used the doubling angle formula for cosine, we used the doubling angle formula for sine, we used the tripling angle formula for cosine, and we used cosine squared plus sine squared equals 1. And all of these are on the formula sheet, but you have to apply them in a sort of nice way in order to go through such a question quickly, right? Any questions about this one? Yeah. The question is, why 4 cosine to the power 3? Yeah, so the question was, why is it 4 times cosine to the power 3? And, all right, so we see 2 here. So that's 2 times cosine squared times cosine. And then here, it's another 2 times cosine squared. Does that answer your question? Perfect. Any other questions? Yeah. Sure. No other questions? Oh, yeah. Mm-hmm. Yeah. That's a good question. So the question was, hey, here you're dividing by c for the simplification, but then we should assume that c is non-zero, right? That's true. That's true. That was me being a little bit too fast, maybe, but I should have said that. So that simplification will only hold when c is non-zero. All right. All right. So then, unless there are more questions, which I thought there weren't, let's move on to the next one. This is one that for me is going to be pretty bad because I'm not much of an artist, and you're asked here to sketch. Now, the idea of this question is not so much that you'll necessarily have to sketch something on the exam, but that you are able to see a formula for a function and then weed out sort of the characteristic parts of that function. So what do you expect to see in a graph of this function? Right, so here's the function that we're going to look at. And this is what we call a rational function. I think it's -4. Yeah. So a rational function is a quotient of polynomials, right? So we see here polynomial in the numerator, polynomial in the denominator. So that's what we call a rational function. And the question is to sketch this function, right? Now, if I want to do that, what I'm going to do, I'm going to go through sort of a step-by-step procedure if I want to graph such a function. First of all, I'm going to note it's a rational function. That already kind of helps my case, because then this step-by-step procedure is going to go quite smoothly. And then the first thing I'm going to do is I'm going to say, okay, so are there some vertical asymptotes that I can draw into my picture? Because then I can start with those lines, I'll have a nice framework for the rest of the picture. So that's the first thing I'm going to have a look at. Are there any vertical asymptotes? And then here I have to say, okay, how do I get vertical asymptotes? Well, essentially, they are caused by quotients, so having 0 in the denominator, and logarithms, having something 0 or negative in a logarithm, right? Or actually having something approaching 0 in a logarithm. In this case, I have a rational function, so the only kind of vertical asymptotes I'm going to have is where this denominator is 0, which means in order to find out where my vertical asymptotes are, I just need to find where x squared minus 4 equals 0. Well, that's a very easy quadratic formula. That just gives me x equals plus or minus 2. So when I start sketching, maybe I'll do it in a different page. That's a good idea. Yeah. Let's do that. All right. That's my x-axis, nice and straight. It's my y. All right. And then here I have my vertical asymptotes. So once I've got my vertical asymptotes, I want to find my horizontal asymptotes. Of course, those aren't usually there, right? Very often you don't have any horizontal asymptotes. And what I really mean by that is I don't necessarily really want to find my horizontal asymptotes. What I want to do is, what I want to know is what happens when my x gets very far away. Right? What happens when my x gets far away from the origin? So I'm not necessarily only interested in horizontal asymptotes, but just in what we call asymptotic behavior. And what that sometimes comes down to, and in particular what that will come down to if we're dealing with a rational function like this, is that we'll get a horizontal or oblique asymptote. So horizontal or oblique. And it's possible you could also get something like a quadratic or a cubic asymptote or something like that. In this case, you won't. But that doesn't really change the question very much. In particular, for a rational function, what we're just interested in here is, okay, what part of this rational function is actually quotient? Because rational functions are always given by some polynomial plus something which is actually a proper rational function. right? So this, what we have here, is not a proper rational function. I can see that because I see that the degree in the numerator is 3, while the degree in the denominator is 2, right? So there's a bit of an overshoot here. What I'm really looking at here is just some linear polynomial and then some proper rational function tacked on. So how am I going to find that? Well, I'm going to do a long division of that numerator by that denominator. All right. So I want to divide this cubic one by that quadratic one, and I see that the first term is 2x cubed, which means I'll need to multiply by 2x, right? Then I get 2x cubed there. So it gives me 2x cubed, and then minus 4 times 2x is minus 8x. And if I subtract that, I get x squared plus x minus 4. Now I've got a quadratic here, I've got a quadratic there, so I have to multiply by some constant, and it turns out, in fact, the constant is 1, right? Because I've got x squared and already x squared there, so just add 1, x squared, and then minus 4. And so I'm left with just x. Right? And now that's of lower degree than my denominator. So I can't really continue anymore. It means that fx is 2x plus 1 plus x over x squared minus 4. And so there I can see now that if I take x very large, either negative or positive, then this x squared will get very, very large. I divide by it, so this part here will be negligible, and most of what I'll see is this 2x plus 1. So out towards infinity, I'm just looking at the linear function 2x plus 1. So let's draw that one in my picture as well. I guess it's gonna be, well, like that. That would be 2x. Can I delete you? Hello? All right. Do this the hard way. So I need to remember to tack on that that plus 1, right? This is what I want. There we go. All right, so that's my oblique asymptote. So now let's draw the function in between. See what I get. If I go in from this side, so I'll go along this 2x plus 1 curve, and then I should go down, right? Because then I get something negative due to the fact that when x is negative, this third order thing here is going to be negative. Right? So I'm going to go to down towards negative infinity. All right. So that's sadly not very well visible here. Maybe I can go down a little bit. So my first part will be like that. All right. Then I'll be coming from plus infinity. I'll be following that thing again, all the way up there. And go down to infinity. And then finally, the rest is not on the screen anymore. But there will be a similar guy like this one up there. Right? So between this oblique asymptote and vertical asymptote. You have a wedge like this. But that intersection point fell off the screen here. All right. Where again, the main part of this is to be able to recognize that these features will be there, that there will be such an oblique asymptote, that there will be vertical asymptotes. And one thing that I didn't really look at now, which is important as well, is where does my function cross the x-axis. I didn't want to spend too much time on that because, as I thought, time goes too fast anyway. All right. Any questions about this one? Yeah. So going by the roots is difficult. Yeah. That's also why I didn't do it now. Didn't do it now. So for a function where, for instance, maybe this was a quadratic polynomial in the numerator would be easier, right?
Yeah, I mean, like if it was only one root, the function would be different. So we should know the number of roots to sketch it.
Yeah, you should know the number of roots to be able to sketch it. Yeah.
Yeah, and from this equation, it's like from our knowledge now, it's impossible to find the number of roots.
Yeah. Fair enough. Fair enough, but you can still make a sketch.
Okay, and I'm curious about how do you know that it's gonna like turn? Don't we have to take the derivative and take this analysis of derivative to sketch that?
So you know that it's going to go from one to the other asymptote, right?
Yeah.
And then you can determine just from the degrees of the numerator and denominator which way it's going to have to turn. Does that make sense?
Yeah.
But I think it's a good remark to make. So the question was, wouldn't you have to do some analysis of the derivatives to be able to figure out how it's going to turn? And that's not really necessary in this case, but it is a good general tool. So in order to figure out when your function bends like this, when it turns like that, you can consider where is the derivative going up and where is it going down, and then of course if it goes from up to down, then in between it has to turn. Okay? All right. Let's move on, unless there are more questions. Yeah. This can be very difficult to figure out actually, because that's actually also where the other question was about. You would need to know how many roots it might have, because it could, strictly speaking, jump down here if you want. If you don't know it, you can just randomly draw something or interpolate, yeah. Or of course just plug in some point and see where you end up. Yeah. Sure. Yeah. If you divide by x to the power 3, yeah. So the question is, if you shouldn't there be a horizontal asymptote? Because if you divide the whole thing by x to the power 3 and then let x go to infinity, so you mean you divide the numerator and the denominator? In other words, you multiply by 1. So the only problem there is if you divide the denominator by x to the power 3, then you get 1 over x minus 1 over, or 4 over x cubed, and that actually goes to 0 as x goes to infinity. So then, well, you're dividing by 0, and then things become tricky. Okay? But to be fair, these are kind of, computations are actually what we're going to cover in calculus, so that those are not part of the selection procedure. They'll be part of the curriculum instead. Okay. If there are no further questions, then we can move on to integration. Where again, my terrible sketching skills will come in handy. So here we have the x-axis, the y-axis, and then the question was about the region between the axis y equals 0, that's just the line y equals 0 is just the x-axis, right? Then there were these two lines, x equals pi over 3, minus pi over 3, and x equals minus pi over 6, that's there. And then the line, or the curve, y equals cosine of 3x plus pi. So what does cosine of 3x plus pi look like? Well, at minus pi over 3, that's cosine of 0, which is 1. So then we're up here at 1. And at minus pi over 6, that's cosine of pi over 2, which is 0. So this goes down like that. And then there we go. That's our final curve, and we wanted to know what the area is inside that inside these four curves, right? So this blue wavy curve, the two red ones, and this blue straight one. And as I mentioned, that's just integrations, right? So the question is really just integrate this function cosine of 3x plus pi from minus pi over 3 to minus pi over 6. Which means we have to find an antiderivative of this function cosine 3x plus pi. There are a bunch of antiderivatives on the formula sheet as well, the standard ones. In particular, we know that the antiderivative for the cosine is just the sine, right? Because the derivative of the sine is the cosine. So the only thing that we have to deal with then is this 3x plus pi that we have inside there. And now we might just say, okay, maybe an easy guess is, okay, I'll just look at sine of 3x plus pi. Right, if the antiderivative of the cosine is the sine, then maybe the antiderivative of cosine 3x plus pi is just sine of 3x plus pi. And we can check by taking the derivative of this guy. And then we see that we'll need the chain rule, right? So the chain rule says that, if we just recall the chain rule for a moment, it says that the derivative of a chain of functions, a composition of functions like this, that's the derivative of the outer function f composed with the inner function times derivative of the inner function. right? So if we apply that here, our f our f is sine of x. And our gx is 3x plus pi, right? Because then indeed, f composed with g would give us exactly this sine of 3x plus pi. So if we just apply the chain rule now, we take the derivative, we get the derivative of sine of x, which is cosine of x, composed with 3x plus pi, so that's exactly what we wanted, times the derivative of 3x plus pi. The derivative of 3x plus pi is 3, right? It's just the slope of that linear function. So that's times 3, which is not quite what we wanted, right? We wanted that thing without the 3. Now, one nice rule about taking derivatives is that if you have some function, right? So maybe we can put down here. So we have some function f, and we multiply it by constant c, and take the derivative of that whole thing, then that's just the same as taking the derivative of that function times that constant. So those constants just keep going out to the front, which means if we had multiplied that sine 3x plus pi by a third beforehand, and then taken the derivative, then that third would cancel against that 3. And then we would have gotten our cosine 3x plus pi that we wanted, right? So in other words, now we found our antiderivative. So our antiderivative of cosine 3x plus pi is 1/3 times sine of 3x plus pi. What we're doing here is a baby version of the substitution rule, which is one of the topics that we cover in calculus in the second quarter. This version is quite easy to sort of derive on the fly. All right, what does that mean here? It means that I should expand page. Now I know the antiderivative, so I get 1/3 sine 3x plus pi from minus pi over 3 to minus pi over 6. So if I plug in those, values, let's start with minus pi over 6. That gives me 1/3. Am I doing this correctly now? Yeah. So 1/3 times sine of pi minus 3 pi over 6. So that's sine of a half pi. Minus 1/3. If I plug in this minus pi over 3, I get sine of 0. Sine of 0 is 0, and sine of pi over 2 is just 1. So I get 1/3. So that area that we see up here, that area is 1/3. All right, so that's our integration question. Yeah. Sure. Scroll down. Any other questions? No other questions. All right. How much time do we have left? 10 minutes. You should be able to do a bunch more. So if there are no more questions, then we can move on to the fifth problem, which is an optimization problem. So we got a function here. E to the power product 2 minus x times x minus 1. And it's given in the exercise that this has a maximum. And then the question is just find both where that maximum occurs and what the value of that maximum is. Now, to do that, we just need to remember that if a continuous function like this has a maximum, then it has to happen at a critical point, which means that the derivative at that point has to be 0, right? Because if the derivative was not 0, that would mean that there was some direction in which it was increasing and some direction in which it was decreasing. So we know that the derivative has to be 0. So if we compute the derivative here, we again have to deal with this chain rule, right? We have a chain here of the function e to the power x and the function 2 minus x times x minus 1. The derivative of e to the power x is easy, it's just e to the power x. We get e to the power 2 minus x, x minus 1, times, and then the derivative of this 2 minus x times x minus 1. So let's consider what that is. See we have. That's 2x plus x, that's plus 3x. Minus 2. Right, so if we work out those brackets, we get minus x squared plus 3x minus 2. Take the derivative, we can do it term by term, right? So the derivative of minus x squared, the 2 comes out in front. So we subtract 1 from the exponent, we get minus 2x. For 3x, we get 3, similarly. And so we get 3 minus 2x here. Right, the derivative of constants just 0, right? There's no slope for a constant function. So we get 3 minus 2x. That's our derivative. And then in order to find the critical point, we need to know when is this derivative 0, right? When is my function stationary? So when is this 0? Well, there's two parts here, two factors. This one is always positive because it's an exponent. It's e to some power. It's always going to be positive, right? It's always above the x-axis. So that's hopeless. So we have to look at that one. When is that 0? Well, that's when x is equal to 3 over 2. So the derivative is 0 at x equals 3 over 2. Since we didn't find any other point, we can kind of assume now that this is where the maximum must occur. In general, you should check whether it's actually a maximum, because the same would hold for a minimum or for an inflection point. Right? So we need to determine by looking at the second derivative whether it's actually a maximum or minimum or an inflection point. And we do that, we take a derivative again. Same thing goes, right? But now we have to also use the product rule. So the product rule, to remind, says that the derivative of a product of functions is the derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. So in this case, we take the derivative of this first factor times 3 minus 2x. But the derivative of this first factor is this whole thing. And so that just gives us this. And then we get plus e to the power 2 minus x x minus 1 times minus 2, right? That's the derivative of this part, it's just minus 2. And so then we see that if we plug in that critical point we found, that 3 over 2, into this second derivative, here it will be 0, right? Because 3 minus 2 times 3 over 2 is 0. And so we're just left with this part. 2 minus 3 over 2 is a half. 3 over 2 minus 1 is also a half. So we get a half squared here, which is a quarter. So we get e to the power 1 over 4 times minus 2, which is smaller than 0, and therefore indeed it's a maximum. Right? When the second derivative is smaller than 0, you're looking at a maximum. When it's greater than 0, you're looking at a minimum. And when it's equal to 0, you don't know. It's inconclusive. So, this is a maximum. And then actually we already also computed the value at that maximum in between here, right? Because this thing here is exactly the function value at 3 over 2, which was our maximum value. So our maximum occurs at x equals 3 over 2, and it takes the value e to the power a quarter, which, if you want, you can also write as the fourth root of e. All right. So that's our optimization question done with. I'm just going to go on until you stop me. I think I can do at least one more. All right, perfect, perfect. We'll have time. We have plenty of time. Unless there are questions, by the way, I won't, of course, move on without taking questions about optimization. All right. So the next question was about an object that is moving along some trajectory, where that trajectory was given by the coordinates as a function of time, 8 plus 2t for x, and then t squared minus 1 for y. And then the question was, when does this object go in the same direction as the line 6x minus 2y equals minus 2, line given by that equation. Now, first of all, to figure out what the direction of that object is, at a given point, you just take the time derivative. You just take the time derivative of this whole thing. So if you take the time derivative of this first one, you just get 2, right? The derivative of 8 plus 2t with respect to t is just 2. And if you take the time derivative of t squared minus 1 with respect to t, you get 2t. Which means at time t, this object is going in the direction of the vector with components 2 and 2t. So then we have to work out when is this parallel to this line, 6x minus 2y equals minus 2. And if it's parallel to that line, it might be as well be parallel to a parallel line. All right? So we might as well just have the right-hand side here be 0. Right, that's just a parallel line. That doesn't change anything. Except that now this vector would actually be on that line. So then I can actually mount an equation here which says that 12 minus 4t has to be 0, right? So I plug my x component here for x. 6 times 2 is 12. My y component for y, so minus 2 times 2t is minus 4t, equals 0. And now I've got a nice linear equation which tells me that this happens at time t equals 3. Right, where the main thing to go in here is just to figure out what is the direction that that object is going in. You can get there by taking derivatives of the components with respect to time. Any questions? And since we got a little bit of an extension, we can actually look at the, yeah. I think the question is why I replaced -2 by 0 here. Yeah, because the question was when is that direction parallel to that line? And then that choice of -2 is just to confuse you a little bit, because of course if it's parallel to this line, then it will also be parallel to any line that's parallel to it, right? And this right-hand side of that equation just changes your line to a parallel one. Okay? Yeah.
I'm just a bit confused because with -2 we get a different answer for t. Like if you like apply like -2 like instead of 0, we get different t. How is it really explained?
Because this vector, if it's going from the origin to this point, right, then it will not be on the line where equals -2, right? Because that line goes, sorry, it doesn't span that line. It doesn't point in the same direction as that line. Does that make sense? So the question was, if I put -2 here and I then would plug those things in the equation, I get a different answer. So why is that? It's because what I want here is I want this vector here that's going from the origin to this point. I want that vector to be in the same direction as the line. So I want it not to just to lie on the line, but to be in the same direction as the line. And then I really need that line to go through the origin. I guess I don't have time for that final one. Yeah, let's not do it. So there was one more question about some sort of optics question. And maybe I'll just make the, how about that? I'll just make the drawing, and then you guys work out the explanation that goes with it. We'll do it like that. I'll just draw this nice drawing. So we'll get this. Let's see. Yeah. Yeah. So I think from this drawing, you should be able to connect some dots, hopefully. And then you can learn more about logics instead. All right. Unless there are any questions, we can move on to the next lecture. Yeah. Yes, it's 1.25, minus 1.25. So this point here is at x equals minus 1.25. Yeah. Sorry? Avoid using a point? I think I don't completely understand the question. Can you avoid using?
Can I solve this without using any points or such, just pure angles?
You can solve it however you want. Yeah. Okay. To me, it's all points, so I don't. Like an angle is at a point, so I don't see how you can do it with that. But you can solve it in any case. In mathematics, you can solve it however you want. If it's correct, it's correct, right? There's no other rule. All right. So here you can see actually you wouldn't really need it because you can consider this tangent to alpha. So in any case, you would get something like tangent alpha equals some slope, namely minus the slope of this line. And then tangent 2 alpha would be 1 over d. And you can always write tangent 2 alpha in terms of tangent alpha. So you never really have to work out what alpha itself is. Okay? So the question was, would this always work? Because you have to figure out somehow what alpha is. I think that was the question, which is hard because what is the arctangent of a half? And if it's a more general value, what's the arctangent of that? That would be, you definitely need a calculator for something like that. And my answer was, well, actually you can avoid computing alpha altogether. Because you know that tangent of 2 alpha, you can rewrite it using the doubling angle formula for the tangent in terms of tangent of alpha. All right.
All right. Thank you very much, Nick.
Of course.
With that, it's time to take a short break. So you have 15 minutes to stretch your legs, visit a bathroom or whatever else. On my clock, I think it's 15:07 now, so 15:22. We will be back for reasoning and logic. I'll see you in 15 minutes. All right. If everybody can find their seat again, we can get started again. For the people at home, get yourself comfortable. Time to do some logic. All right. As the last few people find their seat. Cool, cool, cool. So, before I begin, take a good look. This is my colleague Josephine. You may have already had emails from her. She's wearing one of our TU Delft shirts. After I'm done, if you still want to talk to some of us, we will be in the canteen of this building, the cafeteria of this building, and all of our TAs will have a similarly colored TU Delft shirt on. So look for that color shirt if you have some questions that you want to ask us. Or look for me, I don't have one of those fancy shirts, but hopefully you can recognize my face after seeing it for an hour. So, cool. Thanks, Josephine. All right, then let's get started. So, once again, good afternoon. In case you already forgot, hi, I'm Stefan. I'm a lecturer in the Bachelor of Computer Science and Engineering. And today, I will be talking to you a little bit about a course that I teach called Reasoning and Logic. And the reason I'm talking about it today is that it's also a part of our selection tests. And to prepare for it, we have sent you a link to a free textbook called Delft: The Foundations of Computation. Who of you has already opened this textbook? Ooh, very good. Much better than last year. Okay, okay. For those of you who haven't opened it yet, don't worry. Today is meant to show you that at some point you should open it. But I will try and start from the beginning, so if you've already read a bit in the book, good. The first part might be a bit easier to follow. My goal, unlike the calculus lecture before, is to introduce hopefully some new stuff to you. This is also why I didn't set you homework. My goal is to talk to you a little bit about what I think logic is all about. So for the first 40 minutes or so, we're going to talk about different forms of logic. I have a couple of practice exercises for you. And then in the last 15 to 20 minutes, I want to try and see a little bit about why logic is so important for computer science by zooming in on a few other courses of our curriculum. So I can end up with wrap up with talking about my favorite topic in computer science, the ultimate challenge of computer science. But okay, that's for 40 minutes from now. So for now, let's get started by talking about reasoning and logic. And before I tell you what I think this is all about, I wonder, can you tell me what you think reasoning and logic might be about? Anyone dares to give a suggestion? Yes.
As I see it, it's just trying to express knowledge which we express through language through the mathematical formulas.
Ooh, very nice. Trying to express our human knowledge, which we normally express in English or in Dutch or German, Romanian, whatever else. Trying to express that into some sort of mathematical language. Very nice answer. Yes. What else might we do in this course? Okay, yeah. Applying a bunch of rules and rewrites and stuff like this to get to an answer, some sort of formulation to get somewhere. Yeah. One more? Solving puzzles. Ooh, the perfect one to end on. Because yes, if you ask me, reasoning and logic is about only one thing. It's about puzzles. And I love puzzles. You might be familiar with this one. You're at the side of a river, and you have three things that you want to take across with you. A wolf, a goat, and a piece of cabbage. But your boat can only take one thing across at a time. And if you leave the goat and the cabbage together, you're not going to have any cabbage left. And if you leave the wolf and the goat together, well, let's just say it won't end too well for the goat. So the question is, what do you do? Well, as the author of this comic explains, you first take the goat across, and then let's just say he takes things in a different direction. So to me, this is what reasoning and logic is all about. Fun puzzles and fun ways to solve them. But okay, I teach at a university. I can't really say everything is just about puzzles, though I really try. No, I teach at the university, I teach you computer science. Okay, so maybe we should take a very brief look about what this science might actually be. And don't worry, I don't plan to start a big debate about the philosophy of science, although I'm available in the cafeteria after this lecture if you're interested. Now, for today, I would say that science is the existing knowledge that we have and the process with which we can acquire new knowledge. Okay, and this second part, the process with which we acquire new knowledge, I would say that's what logic is all about. Because, for the purposes of today, I would define logic as a collection of techniques that allows us to acquire new knowledge from existing knowledge. I don't know about you, but that reminds me of a puzzle. More specifically, it reminds me of these types of puzzles. Who has seen these types of puzzles before? Ooh, very, very nice. Cool. In these puzzles, we are given some information, some clues, then a weird grid matrix thingy, we fill it out, and then if we did it correctly, we get to the solution of our puzzle. Now, to me, that's exactly what logic is about. We take some existing information, our clues, we apply a technique, the matrix grid thingy, and we get new information, the solution to our puzzle. Okay, so science is knowledge we've got and the process with which to acquire new knowledge. Logic is a selection of collection of techniques, puzzles. I can see that some of you, your attention has drifted away a bit, and you're probably thinking, why on earth should I care about this? Well, maybe I can give you a reason to care. Who can tell me what this is? A processor, a CPU. It is the thing inside my phone currently screaming along, doing thousands of calculations every second just to keep WhatsApp running. It is the thing inside this little clicker that allows me to do this. And who can tell me what this is? Minecraft? More specifically than that, any clue? A computer or a CPU built in Minecraft. Yes. Now, if you forget everything I'm going to tell you about logic today, and maybe you decide, logic, this isn't it for me, that's okay. Maybe, just maybe, after doing all of this, you are able to decipher these things. Yes, the quality is crappy again. Good. This is in style with the Minecraft story, of course. So, what we see here are two logic gates. Logic gates. And a CPU is built up of just a whole bunch of these things. Logic gates, reasoning and logic. A CPU, the reason this thing and this thing, the reason they work is because of CPU, and they're built of logic gates. Okay, maybe studying logic has something to do with computer science. Good. But if you forget everything I tell you, well, maybe, just maybe, you can build a CPU in Minecraft. Yes. And with that very lofty goal in mind, let's get started. Let's get started by talking about logic, and I'm pretty sure that in every set of lectures ever given on the topic of logic, this guy showed up. This guy is called Socrates, and Socrates suffered a most unfortunate fate. He is the man destined to die. Because there is a very famous argument that goes like this. All humans are mortal. Socrates is a human. Therefore, Socrates is mortal. He will die. History has since proven we were right. Hooray for logic. Perhaps not so nice for our friend Socrates. But again, this argument shows exactly what logic to me is all about. We take some existing knowledge and we derive some new knowledge from it. Perhaps not the most exciting new knowledge, arguably even a bit morbid, but new knowledge all the same. And hey, we've got to start somewhere. In fact, we're going to start with something that is an even more basic form of logic than this argument. We're going to start by talking about something called propositional logic. Who has heard of propositions before? Very good. Maybe you opened that book, or maybe in a philosophy class. A proposition is a statement that is true or false. There is no other option. Examples. You still know what I'm talking about. This is either true, and I really hope it's true, or it's false, which would be very unfortunate. I have a pet rabbit. Could be true, could be false. Proposition. I happen to know it's false, but it could have been true. Lawyers do battle in court. Could be true, could be false. Propositions. But these propositions, in the form of an English sentence, I don't like them much. I want to formalize them a little bit. And this is also where I have a small confession to make. You see, I'm not a huge fan of the English language. Now, don't get me wrong, I like Dutch even less. But the problem with any natural language is that it's very easy to be very vague, very ambiguous. And my machine can't handle that at all. So I would much rather get rid of the English and talk about variables, like in mathematics, so that I can actually do computations with these things. So for example, I have a pet rabbit, I'll just call P. The other benefit is that as a computer scientist, I have been trained to be lazy where I can be, and writing down a single letter instead of 4 words, big improvement. Also, if I now want to say that I do not have a rabbit, all I need to do is add one symbol. It's this thing. It probably has a fancy name. I don't know it. I just call it the weird hook thingy. So weird hook thingy P, which we usually read as not P, means that P is not true. Okay, so an English sentence, we get rid of it, we have a letter, maybe we add in a hook thingy. Now what? Well, these sentences, these propositions on their own, are usually not that interesting. Things become a little bit more interesting if we start combining propositions. For example, if I have 2 things, let's call them P and Q, and I want both of them to be true. I say P and Q should be true. We denote this with this thing, which in Dutch we would call a dakje. In English we would call it a wedge, but we can just read it as and, so we read it as P and Q. And we use that when 2 things should both be true. Example. I wear a top hat and do not leave puzzles unsolved. Wearing a top hat, let's call that P. Leaving puzzles unsolved, let's call that Q. Who can tell me what this sentence would read in logic? P, and then the wedge, right, for the and then Q, or something else first? The hook thingy, and then the Q, yes. P, wedge, hook thingy, Q, or in more normal, more accepted English, P and not Q. 2 things that should both be true. Okay, but what if I have 2 things, and at least one of them should be true? Well, we can do that too. We call it an OR. P or Q, denoted by this thing, which we call V, because it looks like the letter V. We're very creative when it comes to naming. And we just read as OR, so P or Q. And P or Q is true when P is true, when Q is true, or when both of them are true. When you get to studying later and when you open that fancy book, you will find that this thing is called an inclusive OR, and there's also a thing called an exclusive OR. But that's one you can study later. For the last one that I want to introduce today, we denote it with an arrow. It is called an implication. If P is true, then Q is true as well. P implies Q. Example. If I wear a top hat and do not leave puzzles unsolved, then I drink tea. We already had P for wearing a top hat, Q for leaving puzzles unsolved. Let's introduce R for drinking tea. Who can tell me what this reads in logic? Very nice. P and not Q implies R. The only thing I'm going to do is add a set of parentheses here, these round things that we also have in mathematics, to group things together. For those of you that opened that book, technically we don't need them because a conjunction, fancy name for and, takes precedent over the implication, fancy name for the arrow. But okay, I always forget. I only have one teaching assistant. She knows all the precedence rules. I don't, so I just add parentheses everywhere. So also here, P and Q implies R. If I wear a top hat, P and wedge, do not, hook thingy, leave puzzles unsolved, Q, then, arrow, I drink tea, R. Okay, so what have we done so far? We took some English sentences, we replaced them with letters, and other useful words like and or and if then, we replaced with symbols. And somehow, all of this is supposed to help us. Why? Well, now that we've done all these steps, we can create tables. And not just any tables, we can create truth tables. And a truth table is a table that shows all possible combinations of variables for a blah, 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 blah. A truth table is this. Given a formula, in this case not P, we take a look at all the variables that appear in it. Okay? There's only one. There's only P. Then we take a look at the different values that P can take. Well, P is a proposition, and propositions are either true or false. So we denote those with a 0 for false and a 1 for true. Now, if P is false, not P is true. And if P is true, not P is false. There we go, our first truth table. Again, for the negation, for this not thing, not the most interesting. Let's take a look at some of the other operators we've seen. We've got P or Q. Okay, now we have two variables. Each of them can be true or false. So now we have 4 options altogether. I've listed all the options here. When P and Q, the operator we're looking at is P or Q, and I told you P or Q is true. If P is true, that's the third row. When Q is true, that's the second row. Or when both of them are true, that's the bottom row. So the truth table for this thing is a 0 followed by 3 ones. And now for that last one of today, the implication. P implies Q. Now, although I hate to admit it, an English sentence can probably help us out. So as an example, let's take another classic example from logic. If it rains, the street is wet. And now let's take a look at the scenario highlighted in red. In this scenario, P is true, so it's currently raining, but the street is not wet, because Q is false. In this case, when it is raining and the street is not wet, who believes the implication? Who does not believe the implication? Who says no clue whether to believe it or not? Fair enough. In this case, I would also not believe the implication. The implication says if it rains, the street is wet. Currently it's raining, street's not wet. Implication must be wrong. Now let's look at the bottom scenario. It's raining and the street's also wet. Who believes it? Who doesn't believe it? No clue. Fair enough. I agree. In this case, I see no reason to doubt it either. But what about these first two scenarios? In these first two scenarios, it's not raining at all. So in this case, who believes the implication? Who does not believe the implication? Who says, I have no clue whether to believe it or not? Yeah, I agree with the last group. The implication says if it rains, the street is wet. Currently, it's not raining, so I don't know if this implication is true. But in the world of propositional logic, we have true and we have false. We don't really have an option for I don't know. So we have to put something here. Now there's a very nice, very mathematical reason as to why in these scenarios we decide to put a 1 in the truth table here. But I'll save that for when I see you for the real reasoning and logic course. For today, the following argument will do. If we have no reason to doubt the implication, no what we call counter-example, then we will believe it. Now, I cannot stress enough that this is not good life advice. Please be a bit more critical outside of the world of propositional logic. But for the purposes of today, it will do. Okay, English sentences. We got rid of them. We introduced letters, symbols, and then we made tables. Why? Why did we go through all this work? Well, now that we've gone through all of these steps, we can finally make bigger tables. Great. We can combine them. First, we take a look at the stuff between parentheses, we fill out those columns, and then we take a look at the next operator and, After doing all this work, we've come across an interesting truth table. We've come across a formula, a proposition, that is always true. And we call such a formula a tautology. Now, why is this relevant? Imagine you're writing a piece of code. And you're writing some code that says, computer, if this thing is true, please go and execute that bit of code. And over time, you add more and more and more conditions to this thing. At some point, it's become a real mess. Computer, if this long and messy expression is true, great, go and do this bit of code. Now, you take a piece of paper and a minute, you write down a truth table for your long and nasty expression. You find out that this thing is actually a tautology. That means what you're asking the computer is, computer, if this long and nasty thing, which is always true, is true, go and do this bit of code. Well, that means you can just simplify your code to, oi, computer, go do that. Unfortunately, oi is not a keyword that most languages recognize, but I'm sure in Python there's a library for it. Now, that's nice, but that's not the real reason I introduced this example today. The real reason I introduced this example is so that I can show you this slide, which is a real slide from the real reasoning and logic course, which is a little bit more formal than I'm being today. It says a formula A is a tautology if and only if, so no, this is not a typo, if and only if A is true for all possible assignments of true values to its constituent proposition variables, i.e. in all situations. Yay, a formal definition. Students love those. Fortunately, we can usually rely on an XKCD to drive our point home. And if we have a name for something that's always true, maybe we also need a name for something that's always false. And so we do. We call those things contradictions. And if you know how this guy is related to contradictions, then good. You have an excellent taste in video games. So all of this work, English, letters, symbols, tables, bigger tables, just so that in some cases I might get lucky. And it turns out this thing is a tautology or a contradiction and I can simplify my code a bit, doesn't really seem worth it. Well, fortunately, there's about 1 million other things you can do with truth tables. Turns out we can use them to efficiently design our electronic circuits. And I'm not exaggerating when I say that efficiently creating truth tables could be the solution to curing cancer. But more on that later. For now, I want to show you one other application of truth tables. We can use truth tables for what we call equivalence testing. We can use them to figure out whether two formulas mean the same thing. We say two propositions are logically equivalent if and only if, again, not a typo, their truth tables are identical. What does that mean? Well, it means that, for example, these two formula, P implies Q and not P or Q, they are equivalent because their truth tables are the same. These two formula, P implies Q and P or Q, they are not equivalent because their truth tables are different. Using these equivalences, we can find a whole bunch of rewrite rules, just like how mathematics has got them. Take the root of a square and hey, we can simplify it, great. Using these equivalences, we can define a bunch of rewrite rules that allow us to simplify our propositions as well. And when you start studying using our book, I think you'll come across like 8 or so equivalences that are commonly used to simplify formula. The most famous ones being De Morgan's laws. Okay. So far, for a brief, for whatever definition of brief you might want to use, introduction to propositional logic. A logic that is all about statements that are either true or false, no other option. But for the test, you will also be studying a different form of logic. Because as it turns out, propositional logic, great as it is, does not allow us to do stuff like this. Who can tell me what this is? It looks like some sort of group theory. Yeah, sure. It's a proof. Do you know what it proves? Do you know what it proves, this statement? No, fair enough. 1 plus 1 is? 1 plus 1 is 2. Yes, excellent. Yes, yes. It is a proof that 1 and 1, when you add them together, equals 2. You can find this proof on page 379 of a book called Principia Mathematica. A book in which the author tries to build all of mathematics from the ground up, rooted in logic. And it takes 379 pages to come to the hopefully inevitable conclusion that 1 plus 1 equals 2. As the author remarks, the above proposition is occasionally useful. Yes, I'd say so. Notice also that the author says, from this proposition it will follow, when arithmetical addition has been defined, that 1 plus 1 equals 2. We're not there yet. We don't know yet how to add numbers together. But once we get there, we can use this proof to show that 1 and 1 equals 2. Great. And this is a proof we can write because we know a little bit about set theory, okay, I won't be talking about that today, and predicate logic, also known as first-order logic. Now, I just spent 30 minutes talking about propositional logic. Good. I will now spend one slide, about 5 minutes, talking about predicate logic. Far too short, but fortunately, you get a book to help you through. In predicate logic, we don't talk about statements that are true or false, but we talk about objects. And objects can be represented using single letters, and they can either be constants or variables. In the world of predicate logic, I'm just an object. In the world of predicate logic, Lyra would also be just an object. This couch would be just an object. All of you would just be objects. And we all have certain properties. Great. But all of us we can refer to using the notation for objects. Depending on the circumstances, I give myself the letter S, but if our friend Socrates shows up, okay, Socrates gets the S, and I'll go for SH or ST or something else. So objects are the main thing in the world of predicate logic. And as I said, they have certain properties. For example, they might have the property of being human, something that we all share. And to denote this, we can say H of L for Lyra is a human, H of S for Socrates is a human, H of SH to say that I am a human, something like this. We could introduce another predicate, T of X, to say that X is a table, and then this thing would have the property T. And there's two ways in which we can talk about objects in the world of predicate logic. We can either make a claim about all things, which we do by using an upside down A for all symbol, or we can talk about one specific thing and say there's at least one thing that has a property with the there exists or there is quantifier. It's a backwards E. Example. There is a human, something we can hopefully all agree on. We could write as there exists an X such that H of X. There exists a human, okay, an object X, and this thing has the property H, the property of being human. This human is also a child, okay? Also, and, we know how to do and, we got that from propositional logic, and, wedge thingy, C of X, and X has the property of being a child. And now for our grand finale in this one-slide introduction to predicate logic. Again, far too short. That's what the book is for, to compensate for the rest. I'd like to say that this human, this child, is liked by all humans. Okay. And for all things Y, if Y is a human, then Y likes X. So there is a thing X. This X has the property H. It has the property of being a human. And it has the property of being a child. And for all things Y, if Y is a human, then Y likes X. All humans like our person. There we go. A one-slide introduction to predicate logic. The world of logic, where all of us are just objects, and we simply start assigning properties to these objects. Now, for the next 5 minutes, I want to go through a few example questions. Questions I've taken from exams in the real reasoning and logic course, but at the level that I think they could be amongst the questions you would get on the numerous fixes test as well. For some of them, I'll give you 1 or 2 minutes to discuss with your neighbors how you would tackle them. I expect that with only having heard me talk about this for 40 minutes and without any time to prepare for by yourself, you might not necessarily get to the answer in 1 or 2 minutes. That's okay. Remember, my main goal today is to convince you that it's a good idea to at some point open the book. Right? So here we go. Which of the following is equivalent to P implies Q and R or not Z? And there's 4 options. I'll give you a minute to discuss with your neighbors how you would tackle a question like this, and then I'll talk you through it. right. So, how could we tackle a question like this? Well, I've shown you one technique today. It's about equivalence testing. So what we could do is we could make truth tables. We could make a truth table for our statement and a truth table for each of the answers and just compare them. And if we do that, well, we'll definitely get to the answer. There's just one small thing. It's 4 letters. All of them could be true or false. And that means my truth table will have 16 rows. For 5 of these things, that's a lot of work I need to do. It will definitely get me to the right answer, though. So if I'm not sure what to do and I want to answer this question, this is a strategy that will always get me an answer. Just make the truth tables. Just make them. Okay. Hopefully with a bit of practice you can do this fairly quickly. But we can also think about it, and rather than doing all the work, if we study the equivalences, which hopefully you will do before the test, you can solve this question a lot quicker by recognizing that answer C is the right answer, and all I've done is applied 3 equivalences. De Morgan's law, a rewrite of an implication, De Morgan's law again, and another rewrite of an implication. And then we get to answer C. Again, you can find the recording of the session also later today. You can use this question to practice with after you've done a bit of practice with the book. One more example of types of questions you could get is something like this. Which of the following statements is true? I give you 4 options. Answers A and B you might be able to reason about a little bit, although today I didn't talk about what sufficient and necessary actually mean. Answers C and D introduce new notation that for today I've put on the slide, but after you've studied the book I would no longer put in the question. These symbols represent divisibility. X divides Y, means that Y is divisible, with a typo, by X. Again, I'll give you 30 seconds to discuss the question with your neighbor, see if you have any idea what I'm even asking you here, and then I'll talk you through it. All right. So in a question like this, you may have already recognized the terms tautology and contradiction. Remember, tautology, something that's always true. Contradiction, something that's always false. Sufficient means a specific type of implication. P is sufficient for Q is the same as saying P implies Q. And P is necessary for Q is the same as saying Q implies P. But again, these are things that are explained in more detail in the book. I'm just going to show the answer for 10 seconds so that later on in the recording you can pause the video there. The answers on the slide are also explained as to why each of them are true or false. So just for the recording, 5, 4, 3. Pause now if you want to see it. 2, 1. All right. One last multiple choice question. This is another thing you'll find. Reasoning and logic is all about puzzles. But if you take it while I'm teaching it, it is also about creatures called coatis, because why not? You recognize pandas here, I hope. The creature in the top left, for example, is a panda. The creature in the bottom left is a coati. They can be wearing magic hats, like the panda in the top left, and they can be carrying umbrellas, like the pandas in the second row. They can also be wearing top hats, like the panda in the bottom right. With all of this information thrown at you, which of these statements about this coati world is true? Okay, lots of symbols. These had something to do with that predicate logic stuff. Okay, so, and then there's another symbol we don't know yet. It's an arrow with 2 arrowheads. Oh, okay. What does all of this mean? Well, the upside down A was for all. So the first statement reads, for all x is a coati if and only if, that's what this arrow represents, there exists a y such that y is a panda and x is to the left of y. In more plain English, all the coatis must be left of a panda, and all the pandas must be left of coatis, must be right of coatis. We can go through similar translations for each of them. And again, this time on the next slide, you can find the answer later. So after you've taken a look at the book, these are some questions you can practice with. 3, 2, remember to pause now. 1, all right. If you want more practice, you can find some stuff here. There's questions as well as answers. These are the questions and answers I normally use on the open days. I've got a few copies of them also here if you really want to have them on paper, but they're the same as the ones you can find there. But in case you're bored on the train ride home, you can maybe already give it a go. There's some stuff with propositional logic on the first page, some puzzles on the second page, and some stuff with predicate logic on the last page. For now, I also have one more on my slide. Here we go. Me and Nick, the person teaching you calculus just now, we're playing a game of tic-tac-toe. Fortunately, we're not that great at the game. In the game, the goal is to get a row, a column, or a diagonal or filled with X's or O's, depending on whether you're playing X or O. We take turns. I put a symbol down, Nick puts a symbol down, and so on and so forth. First person to get it wins. Fortunately, we're not great at the game. So, yeah, you should probably assume we have no strategy at all, unless by putting something down right now, we can win. So if we put something down now to complete a row, a column, or a diagonal with 3 symbols of our type, then we'll do it. But otherwise, I don't know, it might as well be someone throwing darts at a wall, and wherever it lands, that's where we put it. We have no strategy. Now, you come in, and you see that we've only done 2 turns so far, and the board looks like that. An X in the bottom in the middle, and an O in the top right. You go away for a bit, and some hours later, okay, we might not be good at the game, but at least we take a lot of time playing it. A couple of hours later, we're almost done, and the board now looks like this. My question is simple. Who will win? X or O? I'll give you 1 minute to think about it now, but the rest of the thinking will have to happen later. You can, of course, discuss with your neighbor if you want, or just take a picture so that you can discuss it later. All right. For those of you who want to continue exploring this puzzle later, good, because these are the types of puzzles that are usually part of my exams. The one hint I'll give you is try to reason backwards. Try and figure out what was the last move. And if I may quote Sherlock Holmes, once you eliminate the impossible, whatever remains must be the truth. All right. For the last 10 minutes that I've got now, I was hoping it would be more. Well, let's see. I want to talk a little bit about what I've titled the rest of the story. Because everything so far might very well have been the first half of the first lecture of reasoning and logic. Lectures are 2 times 45 minutes after all, and I've been talking, well, for 50, okay. But reasoning and logic has 10 weeks of material, and after that, there's 2.5 more years. So what else will we be teaching you? I want to give you a brief glimpse ahead. First, in reasoning and logic itself, we will, after discussing propositional logic and predicate logic, move on to talking about proofs. Proofs in mathematics. And we will look at things like this. This thing is called a Gaussian sum. It's great, it's very useful. But the reason I really like it is because there's a nice story that goes with it. Some of you may have heard the story before. This Gaussian sum, is named after a guy called Gauss, who you might know from the probability distribution. But this takes place when Gauss was still in primary school. And one day, the teacher came in, and the teacher said to the class, today I would like you please to add together all of the numbers from 1 to 100. So the class started, okay, 1 plus 2 is 3, 3 plus 3 is 6, add 4 to get 10, 5 makes 15, and so on and so forth. But not little Gauss. Gauss just sat there, arms crossed, doing nothing at all. The teacher asked Gauss, why aren't you working on this problem? And Gauss just replied, because I'm already done. The answer is 5,050. Because what Gauss had realized is that rather than doing all of this work, he could take a shortcut. He could multiply 100 by 101 and divide the result by 2 to get to the right answer, 5,050. Unfortunately for Gauss, his teacher did not realize this, and Gauss was made to stand in the corner for being a smartass. Now, we like this thing in computer science, not putting people in the corner for being a smartass, but taking shortcuts. Why do all the work if I can just multiply 2 numbers and divide the result by 2? We love that kind of thing. But on one condition. It should always work. If I put in the number 200 and suddenly this formula breaks, meh, what was the point? And so, what we teach you is that we can prove that such a formula always works. We write a whole bunch of English and a whole bunch of math, and way more English and way more math, to prove that this thing always works. Now that's very nice, but unlike Nick, I'm no mathematician, and I'm certainly not going to train you to become the best mathematicians in the world. No, we're teaching you computer science. So, after reasoning and logic, we move on from proving things about numbers to proving things about these types of things. Imagine, if you will, that this is a very simplified version of the Dutch railway network, and you want to get from Haarlem, the yellow dot, to Amsterdam or to Delft, the blue dot. Let's go for Delft. Why not? Why not? Because that's the journey that I made as a student when I was studying here. I still lived in Haarlem, and I had to travel to Delft by train every day. And let me tell you, traveling by train in this country is an experience. Every week it feels as if new things might happen. Sometimes a train in Utrecht wouldn't depart, and clearly that means my train in Delft can also not go. Sometimes there's leaves on the tracks, and yeah, I mean, those things definitely shouldn't be there. And one time, and I'm still surprised/intrigued by this sequence of events, my train had to make an abrupt stop because there was a trampoline on the tracks. Okay. But what I learned from all these experiences is that sometimes the app from our railway provider wouldn't really know how to get me home. It would say, yeah, sorry, I also don't know, you figure it out. So I thought, okay, I will figure it out. So I implemented an algorithm. It's called Dijkstra's algorithm, so that this machine could solve this puzzle for me, no matter what the numbers looked like today. And it would get me the quickest way to get from here to home. Great. I like that. I like having the machine do the work for me. I like that a lot. But on one condition. It should always work. If at some point this thing is going to tell me that the quickest way to get from Delft to Haarlem is by going to London first, I want to be very sure that that is indeed the quickest way to get there. And so what do? We prove it. Using a very similar technique, a technique called induction, we can show that Dijkstra's algorithm always works. Great. And once you've done that, in courses like algorithms and data structures and algorithm design, you are ready for what I would call the ultimate challenge in computer science. Now, my boss was here just now, but I think he's left already, yeah? He's teaching object-oriented programming. He will probably give you a different ultimate challenge in computer science. That's okay. We all have our own favorites. But for me, this is it. And for this challenge, which we will tackle in a course called Automata, Computability and Complexity, yeah, that's just one course name. For this ultimate challenge, I need you to imagine that you are this guy. You are what we call a traveling salesman. You have all of your goods strapped to your back, and you travel the land, buying and selling your wares. But, like everyone, you come to one inevitable conclusion. There is one city more beautiful than any other city. One city that it's truly worth spending your time in. Of course, that is the city of Delft. So the question you now ask yourself is this: how can I get from Delft to all other cities and back to Delft as quickly as possible? Well, one strategy you might use is this one. Always take the shortest route available to somewhere you haven't been before. If we start in Delft, we have 3 options, a 2, a 3, and a 7, so we take the 2. In a moment, I'm going to give you 1 minute to apply this strategy. But then I want you to do something far more important. I want you to change just one number so that this strategy doesn't work anymore. And if you have a bit of time left, why not try and come up with a strategy that always works? That always gets me the shortest route from Delft through all other cities and back to Delft as quickly as possible. If you do, I've got a big prize waiting for you. So, 1 minute to apply this strategy, to break it, and to come up with one that always works. All right. So, let's see. We start in Delft, And at first we choose between the 2, the 3, and the 7. I already told you we picked the 2. What's next? 4. What's next? 7. 4. 6. 4. 5. And a 3 to get us back home. Excellent. My favorite part of this presentation, a room full of people shouting random numbers at me. Excellent. So, quick question. Did it work? Is this the shortest route? Who says yes? Who says no? Who says, I was not prepared for this question? I have no idea. Fair enough. But remember, that was the problem we were trying to solve. And in this case, it worked. How do I know? Well, take a look at the routes we selected. The largest one in there is a 7. Now take a look at the ones we did not select. That's a 7, 2 8s, a 9, and a 10. Meaning, there's no way that I can take one of the paths we selected, take it out, and replace it with something we did not select, and somehow make our total smaller. We can only make it bigger. So in this case, it worked. Great. But I asked you to break it. So, hit me. How do we break it? The first 4 we go through, make it very big. Yeah, let's make it 2000. Why not? Then we take the 8, and then either we take the 3 to go back home immediately, or we take the 5, and then, yeah, good luck getting home. Yeah. How else could we break it? One more. Yeah, this same 4, I could also turn it into an 8. And now, uh-oh, there's no shortest path. My algorithm, my method, doesn't know what to do. Maybe we need to flip a coin. Oh, it sounds dangerous, right? I was thinking, how about this last 3, the 3 we need to get back home? How about I make that 30,000? Now, I don't know in this case what the right answer is, but it's definitely not this. But maybe you found me a strategy that always works. If so, great. Keep it in mind just a little bit longer. That big prize is coming up. For now, well, I have this machine. Why don't I just let the machine do the work for me? How hard can it be? Well, let's find out. Unfortunately, I don't really know how to solve this, so I'll just try all the options. Okay? Well, nowadays we can travel by plane, so if I have n cities, I can go from any city to any other city directly. I've got my plane or helicopter at the ready. So from the first one, I have n minus options to choose from. I pick one, and I go there. Now I have n minus 2 options. I pick one, and I go there. Which means that in total, we have n factorial. Yes, technically n minus 1 factorial, but trust me, the minus 1's not going to matter in a moment. N factorial options to choose from. Now my machine is incredibly fast. It can check 1 billion options every second. It's pretty good. It's a lot of zeros. Unfortunately, for just 36 cities, it would already take my machine longer than the age of the universe to find the right answer. I don't know about you, but I would like to get home sometime before then. And so clearly, trying all the options doesn't work. So the question is, what does? What is this strategy that always works? And I told you before that as computer scientists, I don't know is not an option we can handle very well. But unfortunately, I don't know is the only answer I've got. And that is what we call in computer science P equals NP, question mark. And simply put, it is the question, what is a strategy to get me the shortest route from Delft through all other cities and back to Delft as quickly as possible? And there's 2 options. Either such a strategy exists, and all computer scientists so far have been incredibly stupid, and we just haven't figured it out yet. Well, I'm a computer scientist. Don't really like that option. The alternative is that there is no solution. There is no way to quickly find such a route. But if this is impossible, then why can't I prove that? We can't do that either. So as computer scientists, we're stuck right here, right in the middle. Every day, someone might wake up and show the world how stupid we've been. Or maybe someone will finally save us and show us how to solve that it is impossible to solve these problems quickly. Now, I've been droning on for a bit, and I'm already 1 minute over time, so I'll try to wrap up soon. And I see that the looks on some of your faces have taken on something resembling this. I can't really blame you. I've been talking about a puzzle that may or may not have a solution, that takes incredibly long to solve on my computer. Okay, why should you care? Well, maybe I can give you a reason. I told you before that if you find me a solution that always works, I've got a big prize waiting for you, and I do. If you solve this problem one way or the other, you'll get $1 million, because you will have solved one of the millennium problems. If you think you got a solution, come talk to me first. Pretty sure we can make that a whole lot more than 1 million. So, is that the reason why you should come and study computer science and engineering at the Delft University of Technology? So that you get your shot at that $1 million? Of course not. This is why you should care. For at this university, I look forward to teaching you a lot of amazing stuff. A lot of amazing stuff about programming, about building large software projects from the ground up, about how to develop code in a reusable, maintainable, and testable way. A lot about all these software engineering practices, about computer networks, about machine learning, and who knows, maybe a bit about blockchains and artificial intelligence. But in this program, we're also going to teach you a lot of amazing stuff about mathematics, about logic, about algorithms and proofs. And that means that in the second year, and I think some of you might see me for that next quarter, you will be in a classroom and someone like me will stand in front of a blackboard talking about the properties of a non-deterministic Turing machine with k finite memory tapes, a machine that cannot exist and that we will never be able to build. And if at that point you are sitting in that classroom and you are thinking this, then I failed in my job today. For it is my job to warn you that amidst all this amazing stuff about software engineering and programming and artificial intelligence and I don't know what else, there's going to be a lot of amazing mathematics and theoretic computer science too. And if you've listened to me today and think, I'm pretty sure I never want to hear anything like this ever again, that's okay too. I won't hold it against you. But this is where we should part ways. Okay, with the serious part over, let's try and recap. Today we talked about a guy destined to die. Okay, maybe that's not the happy note I'm looking to end on. We also talked about these CPUs and how they're nothing more than a whole bunch of logic gates. And if you forget everything that I told you today, that's okay. Maybe, just maybe, you can still build that CPU in Minecraft. And with that, thank you for being here today. I look forward to chatting with some of you in the cafeteria together with our TAs. But if not, good luck finishing high school and good luck on our tests. Thank you.